Okay. I made a mistake. I actually recorded this video. Well, I didn't record, but I actually went through the principles of that we are going to discuss in this video. I didn't realize that I hadn't pressed record. So that's why everything is written already now. But we can go through them without me having to write down everything again. It's slightly long because I think I went for 30 minutes or something. So hopefully this will make it quicker without me having to explain every single bit of what I had explained. But so what we are doing, what we are going to do is in this one, we want to calculate cross entropy perplexity, or we just want to calculate how good is our model doing. As human beings, we can easily do that. We can just read it and say, no, this is not correct English, or this is not correct or grammatically correct sentences and all of that. But these models, they do not understand language. They understand numbers. So we want to convert whatever we are doing to numbers. So we'll do it step by step. But for now, let us discuss how we actually generating how we are generating words. So I'll be using a different color now because it's already written in black, so it'll be difficult for you to follow maybe. So I'll now use orange. We have our vocabulary here that we will have. So in our example, we have seven tokens in our vocabulary. And as you know, a vocabulary will then come with its inverse vocabulary. So an inverse vocabulary is just the way we are doing with our vocabulary is saying token number A is token ID 0, token effort is token ID 1, token every is token 2, and so on. But in our inverse vocabulary, we then just say our token ID to to the actual token itself. That's what we're doing in our inverse vocabulary because it helps us then once we have predicted our tokens that we need to print out, we can then use the inverse dictionary to just get what the actual words are. So here, imagine we have these as the input. So if this is the input, we'll say every, and then we tokenize it. The token ID is 2, and there and here we are going to apply the GPT model. We apply the GPT model, and what comes out are logits. So these are the logits that will come out of our GPT model. So let's, for example, here in our case, the logits will have 7 dimensions because our vocabulary is 7 elements or 7 tokens in it. Because now what we're going to do is we're going to look at the logit that is the highest value or the largest value, which is this. And we say, what is the index of that logit that is the largest value? It is index number 0, number 1. It is index number 1. So our prediction, it becomes predicted tokens. So token IDs. So those are the token IDs that we're predicting. And we go to the inverse vocabulary. We go to the inverse vocabulary. We say which token is the token number 1? It is effort. And then we print this. So this is the word that we print effort. And once we do that, we then add effort to our input. So now we have 2, 1. And we put 2, 1 into our GPT model. And these are the logits that it predicts. Again, we look for the largest one. We see it here. We ask ourselves, what is the index of that one that is being the largest? It is index 0, 1, 2, 3, 4. Index 4. Let's go to our inverse dictionary. I'm just going to use the dictionary, this one here. So index 4 is uh, is the word moves. So our predicted token ID 4 and the word itself is moves. And moves comes here. And we do the same thing. We get 0.34, what token ID 6, 5. And then we say 5, U, that's it. And so on and so forth. That's what we do. But when we have generated this text, we want a way to actually measure how well these ones that have been predicted are coherent. Are they the ones that we really wanted? So here we are using a 7 token vocabulary, but the GPT model works with a much larger vocabulary of 50,257 words. And so it will be much larger. So it will be difficult for us to see here. But let us just create some 2 examples. Here we are going to work with 2 examples. Every effort moves, and I really like. So let us see. When we have those, let's just go to Chrome so we can see in our set this up in our Google Chrome. So in our Google Chrome, this is us setting those up. We have these inputs, every effort moves, and then we have these 4107, 583, I really like. And we have our targets. Our targets are going to be this and that for the second input and this for the first input. But what we can see is the targets, like we always know, the targets are always are always a shift of one from the inputs, right? A shift forward of one. So our targets are just the inputs shifted forward by one, as you can see, because what are we trying to do? We're trying to predict the next word. We're trying to predict the next word. So if we train our model using this mechanism of saying the targets are just shifted by one, we'll be training it to predict the next word. So now that we have that, let us let me see what we if we can do it here or yeah, okay, let's just do it here and then we can go back to smooth draw and explain some of these things. We calculate our model. Here we just put our touch no grad because we don't want it to touch to track any gradients that are being calculated and all of that. Logits, we apply our model onto the inputs and then we get our probabilities, right? Probabilities using soft marks like that from the logits. And it is a shape of two because we have two inputs, each being 3 and 50,000 dimensions because that's our vocabulary size. 3 tokens each, right? And then we can get the token IDs of the maximum ones. So for each one's, what are the token IDs with the maximum values? So these are the maximum values, and these are the maximum values for the second input. Great. And now we look at this. These are the targets that we wanted. We wanted every effort moves you. When we convert the token IDs to text, because we have the token IDs for our target, right? And then our output for the first one, we have token IDs. Let's convert those again to to normal words. Oh no, look at this. They are very different. Our target and our output are completely different. And that is what we are building on that is what we're building towards this in this chapter. How do we measure this difference? How they are different to each other? That's what we want to do. And we know that for us as humans, we can see that they are different. We can read and see that they're different. But these models, they cannot read these words. They do not even know that they are words. They just know numbers. So how do we numerically tell the model that these are two different? That's what we're trying to do. And this measurement would then measure also the quality of the generated text, which is a building block because if we can measure numerically the quality of the generated text, we are able to then use that in training to say if the quality of the generated text numerically is bad, update your weights. Keep updating your weights until the quality numerically is good. Even though we might not know what the words are, but numerically we are confident that numerically that it is good. So that now when we then apply it to convert to words, when we then start generating words, we know that it will have learned how to generate good words. So numerically, the process we are going to use is very simple. Let's actually take back to smooth draw. Okay, what we are going to do is we are going to calculate logits, right? First, we are going to calculate the logits of our prediction, and then we convert those logits to probabilities. We then have our probabilities, right? Here, these are probabilities. And this is just saying it's scientific notation. This is scientific notation. It's saying decimal places, so it's going to be 0.000018. What? It's just a 1/8. It's just scientific notation. It's much easier to write it this way than to write it with decimals like this. And this is going to be 0.000015, and stuff like that. That's what we're trying to do. Now that we have those as probabilities, we then compare with our target probabilities. We compare our output probabilities and our target probabilities. And we are going to use a logarithm. here I'm going to skip this part here because you can Google why we use logarithms. Logarithms are used because imagine dealing with that's one reason. Dealing with these small probabilities, it makes optimization, mathematical optimization, much slower and it's not efficient to deal with these small numbers. So we would rather convert them to logarithms. When you convert them to logarithms, we then uh we then start dealing with numbers like minus 9.5, minus 10, and all of those are easier numbers to deal with than the target. You can Google what is the advantage of using logarithms but in over small decimal numbers. You get some good results there. And then once we calculate these logarithms, we are going to combine all of them into one metric. And the metric that we're going to calculate is the average log probabilities. So we just add up all of them and divide by how many they are. They are 50,257 because of course that's going to be that's the dimension of our logic, right? The size of our vocabulary. So we add up all of them divided by 50,257, we'll get an average. So this is the average log probability, right? So with this average log probability, we then use the negative average log probability. We just multiply this average log probability multiplied by minus one so that we deal with positives. We don't want to deal with negatives. And this process of doing this is what is called cross entropy. And the results that we would have calculated here is what is called cross entropy loss. So for our case, this is cross entropy loss. Is it good? It's difficult to intuitively interpret whether it's good or not. And that is where we have our metric called perplexity. And perplexity pretty much is the exponent of the loss of whatever loss you would have come up with. So in our case, if we do exponent of the loss, we'll get 48,725.823, 8203. So this is our perplexity. In perplexity, it is defined as the effective vocabulary size about which the model is uncertain. So in our case here, when the model is trying to predict the next word, it is uncertain how to choose the next word from 48,000 tokens. And this shows why it was saying armed he Netflix, because it is confused. But it's confused by 48,728 tokens out of 50,000. So this model it's confused. It doesn't even know. It might as well just choose at random because it's confused by 48,000 tokens. If it was confused by 10 tokens out of 50,000, would have been like, yes, this model, we are sure that it is now trained correctly. And then even though we haven't used it to generate text at all, we're just looking at its perplexity score. We will then take that model and then we say, please generate, I'm giving you every effort moves. It is definitely going to give you coherent text like moves you forward one step or whatever it is going to be that it will generate, because it's only going to be confused by 10 tokens out of the 50,000. So it is quite sure what the next token is supposed to be. So that is perplexity. So let us see in code how we are actually going to do this. So we are going to definite, definitely it's a way of just being comprehensive here. We are going to just do what we did in the example. We have our probabilities. When we have our probabilities, we calculate our log probabilities. We're just going to use we are going to use yeah, we have our log probabilities. We are going to use the torch, which is the log there, and we are concatenating the target probabilities for each one of them. So we're saying these are the target probabilities for the first one, target probabilities for the second one. So these become our log probabilities. When we have those as our log probabilities, we're going to do the average. Just get our average. So this is our average probability. Is it good or not? We just convert it to a cross entropy loss. So this is our loss for the whole model. So it's not loss per input or anything. It's the loss for the whole model when it's going through all the inputs. It's going through all the inputs. That is our loss for the whole model. And then now that we have that loss for the whole model, this what we're going to do is to say this. Let us now just do for our two examples that we have. We have two examples with the batch size of with the, each having 3 tokens and 50,000 257 dimension because of the vocabulary size. And our targets, of course, we have two targets corresponding to the two inputs and three token IDs. That's what we want to aim for. So here we're just flattening. We are flattening these so that we can do the calculation from touch. The reason why we are now doing it this way is because we do not want to for everything. Imagine now we have, instead of two examples, we have 50,000 inputs in our set. We do not want to be doing this manually every single time, right? To do those processes, calculate your targets, calculate your log, calculate your average, calculate this. We want to implement things that are already built in touch. So you see, in touch, in functional, there is cross entropy. So let's just get that cross entropy from there. But to do that, we need to have these logits and the targets to have the same shape. So um, so what we're going to do is we're going to flatten the logits on the batch size and the num tokens dimensions. So that's what we're doing here. We're flattening it on those two dimensions, the first and the second dimension. And then we just flatten also our targets. So they just get added into one. So this becomes like one list. This also becomes one list. So now what we have is just 6 tokens each with 50,000 dimensions. And then here we have 6 tokens as well and all of that. So now that it has that, Torch will take care of actually calculating cross entropy, will take care of calculating the cross entropy and the probabilities and all of that. So when you give it logits, it's going to then calculate the maximum index and then just return the 6 index token IDs that it would then compare to the 6 token IDs here. And then it will calculate the cross entropy and all of that. So it happens in the background. You don't have to really think about it. Where we're manually thinking about, oh yeah, what is the index that is the maximum and all of that. Cross entropy handles all of that in the background. So we give it our logits that we have flattened and our targets that we have flattened. And we calculate our loss. As you can see, the loss is the same. And then perplexity, we just do exponent of the loss, exponent coming from touch, and we get our perplexity. So that's just it. That's that part there. And here we're just using two examples. Now let's take this thinking further into actually now when we have a validation set, when we have a test set, so we can see overall how is our model performing when we have all these numbers, all these inputs that we can use to actually test our model. Because now when we have those and we get into training, if you've trained machine learning before, you will have a validation set on the side. And you train your model, and then you calculate the metrics to see how it's doing. So here we're just going to see how to do it for the validation set. It's probably going to be terrible, but then when we now do it for training, when we're now training it, we'll be using the same principle. But let's see the principle in the next video.